Good, good. And hello, everyone. Thank you for joining this NetPlace event. And thank you also, Rakis, to give this talk. So before introducing our speaker, I want to introduce a little bit in general of this NetPlace, because maybe some of you are new, it's the first time you attend this event, or it's also because we slightly changed the structure of this event too. So in the future NetPlace events, in general, we'll have two sessions. The first session is about research, sharing research. And the second session is about sharing difficulties we faced during our PhD. And we can have a free discussion on the plausible solutions for these difficulties. So all of you, you're also encouraged to join our discussion on Twitter, because we will write some summary or discussion on Twitter about this conversation. And if you have any difficulty you want to discuss, feel free to send an email to our mailbox, netplaceorganizers@gmail.com. And you can also follow our YouTube channel. You can just type in a NetPlace on YouTube and you can see this channel, and we will share mostly the talks and discussions on there, depending on if this conversation is very controversial or not, but we will ask for your permission. So let me introduce our speaker today. So Rakis from Indiana University, Bloomington will give a talk about human belief systems and social contagion. Now the time is yours, Rakis.
Great, thanks. Thanks for having me. It's fun, and I'm glad that there's an event like this going on somewhere in the world. And I hope this can be something fruitful and you have something to take away at least. Cool. So I'm going to be talking about, well, human belief systems and social contagion, but I'll particularly be discussing some work we are doing at IU in the space of belief networks and simple and complex contagion. These terms, if they don't make sense to you right now, it's fine. Hopefully it'll be clear as we go along with the talk. And yeah, so I'm Rachit. I just got transformed into a PhD candidate at IU, so that's fun. And I also like going around places to hear how people pronounce my name. My mom can't believe that it's hard to pronounce my name, but yeah, it is what it is. So it's Rachit. And I work mainly with YY, Yonggi Alan. He's my main supervisor. And I have a bunch of other people I work with, but the project I'm going to be discussing today is mostly with Alessandro Flamini and YY. Okay, let's get started. Cool. So contagion is a fundamental phenomena. We all know that. I mean, in the space of pandemic, this is not surprising at all. Just to motivate that example a little further, it's just not limited to biological contagion. So on the right over here, you see an influential figure, in this case, Gandhi, giving an influential speech to society, maybe. It probably nudged them to start thinking differently. On the left over here, this is not COVID, this is the influenza epidemic. So that's as much as about the pandemic I'm going to be talking about. We all have heard more than enough talks about the epidemic spreading models and stuff like that. So that's where I'm going to leave it. But what's interesting is also the space of what I've highlighted in between over here, where there's also this contagion of conspirational thinking, where you have birds not being real, or the flat earth society and stuff like that. And in fact, in one of my previous talks, I did ask, I mean, out of casual humor, I did ask how many of you think birds aren't real? And some people just heckled me to saying that they aren't real and stuff. Okay, cool. So these are some examples of contagion. And split in a different dimension, you can see that contagion is responsible for both good and bad. So on the good side of things, you have social contagion, informing us about impending disasters, teaching us about a lot of new things, climate change, upcoming elections, and all of those things. You have information about that, warning us about disasters and stuff. On the other side, it's also responsible for bad things, bad in the sense of course, good and bad is subjective, but I think we can objectively agree on this being good and this being bad on the other side. So you have misinformation about vaccines spreading around, misinformation about politicians, actors, celebrities, whatnot. You can think about whatever you want to think about. So the way we think about it is the science and technology to spread any kind of information more often than not exists. So that's not a primary challenge as such. It's, I mean, more or less, we reach scientific consensus. It takes its own process, but we do have scientific consensus on a lot of things. And the technology to spread any kind of information, it's already there. You can spread information from one corner of the world to the other corner within seconds today, right? So that's not the primary challenge. So the way we look at it is the primary challenge comes in sharing accurate information and coming to a social agreement. So scientific consensus is very different from coming to a social agreement. I'm making that distinction over here. Okay, cool. So that's probably the main motivation for us to study contagion, I think, right now. So, and this is not new, of course. Contagion has been there for centuries. I mean, centuries is an exaggeration, but for a lot of years, people have been studying contagion and classes of contagion. And just to bring us all onto the same page as to how I think about it. Well, okay, so in most of this talk, I'm going to be saying I, but I mean we in the sense who I work with, okay? Sorry about that. Anyway, so classes of contagion. To understand that, it helps us start looking at this network over here. You have the focal individual, and you have some infected or active neighbors around the focal individual marked on red. And you have some probability of this focal individual getting activated or infected by one of these infected individuals, okay? So one class of contagion, which is commonly known as simple contagion, treats these as independent events. So you're getting infected by this guy or by this guy are independent events. Those are coin tosses in some sense, Bernoulli trials. All right. So the overall adoption probability is a result of these independent events happening. Okay. And it's been known in literature that this sort of contagion, for it to spread, that means a simple contagion class of contagion to spread, you need inter-community links. That means links connecting multiple communities. So it's very easy information to hop from one community to the other and go on that way. Okay, and we have common models like the SIR model or the independent cascade model, which is commonly used to model such classes of contagion. Now, on the other hand, you have complex contagion. And more often than not, when people think about complex contagion, this is something which has often popped up when I discuss this work. They think threshold models. So threshold models are just one realization of complex contagion. It's not the definition of complex contagion. So the definition over here is like a broader, it adopts threshold model as an example, but what it truly is these adoption probabilities are no longer independent trials. So you having interacted with this person over here affects your interaction with the next person over there. So these are correlated probabilities. And these can take various forms of correlation or various forms of interdependencies. But yeah, that's one distinction that's a very fundamental distinction between simple and complex contagion, I would say. So yeah, in one case, in simple case, it's independent trials. In complex case, it's no longer independent trials, okay? And again, it's been known in literature by James Gleason's work also, I think, most recently, where it's facilitated by intra-community links. So you need a lot of redundancies and intra-community ties for complex contagion to spread. And one example is threshold model. So threshold models is not the definition of complex contagion. It's more to do with this dependency and interdependency. Okay. So the characteristic curves of these classes of contagion is indicated over here. On the x-axis, you have some sort of reinforcement, how much of redundancy, how much of extra information you need to adopt some information. And you have the adoption probability loosely over here. So you don't need a lot of reinforcement for simple contagion, but for complex contagion to spread, usually you need a lot of reinforcement. Of course, you can imagine other characteristic curves, but this is popular in literature, I think. Okay. Cool. That being said, hopefully we're on the same page with these things at the moment. So I mentioned that it's important to study contagion. And I showed you all those examples. And I've also mentioned that tons of research has already been done in the space. They've categorized into two classes of contagion and stuff. So why am I here giving yet another talk about yet another contagion model and whatnot, right? So that seems a little redundant. So to justify that part of things, I think it's helpful to understand some fundamental limitations across contagion models, not just like one contagion model, but across a set of contagion models out there. Okay, so this is where I've been, okay, I'm just going to get to it. So most contagion models are disconnected from cognitive theories. So when you model contagion, like the network which I just showed you before, humans or that node is considered to be an abstract unit in some sense. It's like an up vector or a down vector or an up spin, down spin, and stuff like that. So it's not a human at the end of the day. It's just something very abstract. So that is I can say this because I have a background in physics, so I don't mind dissing my own creed. Right, so that's a very physicist approach to things, where you model a curve as a spherical object and go ahead with life. Okay, so that's how things work. And this ignores the entire field. I mean, if you were at IU, I would point to the neighboring building because that's where the cognitive scientists sit. And it ignores the entire field of cognitive science. It doesn't really capture the cognitive complexity humans have in decision-making and information processing. So that being said, so when information comes to you, you just don't blindly reject or accept and pass it on forward. You have some complex mechanisms occurring within you where that information gets manipulated in some sense. Okay, and that is missing in most of these contagion models. So one such fundamental phenomena is cognitive dissonance. And I think we have heard many versions of dissonance from each other, but just so that you're on the same page, this is how I think about cognitive contagion. If you don't see in my background, I'm a huge fan of Federer, and it's been a tough few months because he retired. But so you have Federer over here on this node, you have match fixing over there, and you have a concept of good. So how do I read this system is, I think Federer is good. That's indicated by like a positive link between Federer and good. And I think I think match fixing is bad. That's indicated by a negative link between match fixing and good. Okay. But now there's some allegation that Federer has been involved in match fixing. So immediately you can see some tension in this system over here of mine, where, I think Federer is good, match fixing is bad, but Federer has been accused of match fixing. So how do I like him? Right. So there's a tension over there. So this is dissonance. And there's this whole body of literature in cognitive science which says that dissonance is so fundamental that humans are inherently biased towards resolving dissonances. So when we know dissonance exists, we try to resolve them as much as possible. Okay, so one way to resolve this is I say, hey, no, Federer is not involved in match fixing. Oh, that seems sense. So he's good, match fixing is bad, but he's not involved in match fixing. So all logical sense is happening over there. On the other side, I can totally disconnect from Federer and say that he's a bad person because he is involved in match fixing. And it's true that he's involved in match fixing. So these are very logical things to do, but you can also see some conspiracies popping out of this where I can say that, hey, match fixing is good because Federer is doing it and stuff like that, right? So I justify this own belief system of mine. So this entire complexity in conventional contagion models, when you treat humans as spins or vectors, is sort of lost, okay? And that is one fundamental limitation of our current models of contagion. And on the other side of limitations, in the network science space at least, the dynamics of social contagion is often assumed to be simple or complex rather than it being allowed to emerge from fundamental mechanisms. That means to say, I look at a phenomena out there, I have an event occurring, I'll be like, okay, cool, I'm going to model this as simple contagion because it seems like simple contagion, or I'm going to model it like as complex contagion because it seems like complex contagion. More often than not, I don't have empirical data to actually measure this. And I think you all know some work by Laurent and Peter Dodds and Sam Scorpino in Vermont, which show that it's hard to distinguish the two in empirical data. So more often than not, assuming that one or the other is occurring is incorrect and incomplete in some sense. But that's been the trend in the field. One particular work, again, by some people in our group, is this one, which showed that in a single social system, this is Twitter, both kinds of contagion can occur on the same sort of information. So this is a spreading of hashtags, okay? And you can see that some hashtags spread like simple contagion, and some other hashtags spread like complex contagion. Okay, so that is indicated by these figures over here. So this hashtag, these are communities. The size represents the prominence of that hashtag in that community. And remember, I said that simple contagion spreads across communities, while complex contagion spreads within communities. So you can see during the early and late stages of these two hashtags, they've jumped communities while this one stays within the same community. So this is simultaneously happening in a single social system during the same time period and whatnot, right? So this is like empirical proof that both sorts of contagion are occurring. And now if I model this saying that, hey, spreading of hashtags is a simple contagion process, that's wrong. Or if I say spreading of contagion is a complex contagion process, that's wrong, okay? So there are models which sort of combine the two contagion classes. And there are those kind of models, but those kind of models, again, miss out this cognitive dissonance part of things on the left side of things. Okay, so I hope you're clear on that. And that is where I come in, or again, we come in. So we ask if there can be a unifying cognitive model from which both simple and complex contagion dynamics arise. Okay, so I'm not explicitly encoding simple or complex contagion dynamics into it, but we're trying to allow it to emerge from cognitive mechanisms. Okay. Okay, so that's where the weighted belief network model comes in. And here you have the operationalization of the model, where you have these nodes are individuals in a social system, and they're linked to each other by some social ties. And within each individual, there's a belief network or a belief system. And the nodes of the belief system are concepts, which means Federer, good, match fixing, Donald Trump, vaccines, whatever you want it to be. And the edges are beliefs. So it goes back to that example which I just showed you. Okay. And these edges are weighted and signed, meaning positive beliefs and negative beliefs and how strongly you believe between the two concepts and stuff. Okay, so this is the operationalization of the model, and that's what we call a belief network. And each individual in the social system has this. So when information flows between individuals, it just doesn't blindly flow, but it needs to do something to this belief system within that individual. Okay, where the information is manipulated. And the stability, so it's important to capture cognitive dissonance, it's important to realize, how do I measure cognitive dissonance of each individual? And that is done using social balance theory, which again has empirical justification to it. Like there's proof that, this is how things work in humans. So these are stable triads. I mean, okay, so to measure the stability of an individual, I calculate the stability of the belief system of that individual, which means I measure the energy of that belief system. And the energy is just the product of these edges of the belief system. So if I have a triadic belief system, I have the product of these edges to be positive. That means the energy is negative because that fancy little negative term over there causes physics. And unstable belief triads have positive energy. Okay, so you're biased to being in stable states. That's your cognitive bias. And you don't want to be in unstable states at the end of the day. So that's how visually it looks. And now I'm going to explain the model dynamics. This is the bias again, where you want to be in a very low energy state. Okay. And think about an example to motivate the dynamics. So here's an individual's belief system. And this is unstable because the product is negative. So that means to reduce your energy, this belief should flip towards blue side. Okay, that's what this derivative implies. So when you have a stabilizing piece of information from your neighborhood, this is from my neighborhood, this is going to stabilize me. So I'm very prone to accepting that stabilizing information. On the other hand, if I'm already stable, and I have a destabilizing information, I'm a little resistant to accepting that information. Okay, so that's the intuition behind what's going to happen with belief systems. So yeah, and this is governed by these three rules, I think. This is the master update rule, where the belief at the next time step is the belief at the current time step plus some update. And the update in the model is picked from a normal distribution. Now, this need not be a normal distribution, just to introduce stochasticity and stuff. It's picked from a normal distribution with some mean and variance. Again, this is just nothing unique about this distribution. And the mean is, this is the heart of the model. The mean is the competition between your social influence and your own internal desire to be in a coherent state or in a stable state. So if both these things point towards the same direction, you're prone to accepting it. If they point in different directions, you're less prone to accepting it. Okay, so far so good. And the next two slides are going to go into the results of the model, where you have this experimental setup. It's a star graph. And in the center, the hub is an unstable belief system. And your neighbors is a mix. So some of your neighbors are stable, some of your neighbors are unstable. Okay. And similarly, you have a stable belief system. And some of your neighbors are the stable of the same kind. And some of your neighbors are also stable, but of a different kind of stability. Like both these belief systems are stable belief systems. So in order for me to accept that stable belief system, I need to temporarily leave my stability, go towards instability, and accept that, right? Similarly, over here, if I have to accept a stable belief system, it's very easy. I just have to flip one of these edges. Okay. And I run the belief network model on this, and I ask this question: what's the probability of hub flipping with the number of neighbors of a different kind? Okay, so what's the probability of this guy flipping given the number of these kind of guys? And that's how the curves look, the result. Okay, so you can see in case of me being unstable, and if I have a stable stabilizing influence, I need very little reinforcement to flip me. But if I have a lot of, if I'm already stable, I need a lot of reinforcement for me to leave my stability and then come to a different stable state. So I need a lot of reinforcement to flip me. And these, if you remember, the characteristic curves of simple and complex contagion. We've done a little more experiments to verify that these are indeed simple and complex contagion curves. It's more to do with the concavity and the convexity of these curves and stuff. Okay, and this is like first proof saying that I have not encoded in the model explicit simple and complex contagion dynamics. It emerges fundamentally or organically from cognitive mechanisms. Okay, so now you might call me out saying that, call us out saying that, you know, this is a star graph setting. Real world social networks are not star-like. You know, there's a little richness to that network structure and stuff. So to verify that, here's what he did. This is a block model setup, two communities. I'm throwing out these terms like block models, etc., assuming that all of you guys are familiar with it. But anyway, block model setup, two communities. Omega governs the mixing between the two communities. So omega 0.5 makes it a random network. Omega 0 isolates into two communities. Okay. And what this paper over here did a couple of years ago is they ran a purely complex contagion model on this network. So they infected a few individuals in one community. They ran a complex contagion model and saw how the information spreads. So on the, let's see, both of these are like equivalent curves. So maybe it helps to see on the bottom curve over here. So omega governs the mixing factor. Rho infinity governs the final fraction of infected individuals. Okay, that means if I infect a certain number of rho naught individuals, if I infect 1% of the population, or 10% of the population, sorry, what's the final number of infected individuals, or what fraction of the population is finally infected? And you can see over here, there's an optimal regime of mixing when the entire population gets infected. Too much mixing, and you don't have enough reinforcement for the contagion to spread. That means in a random network, you don't have enough reinforcement for the contagion to spread. Too little mixing, that means it spreads only in one community, but it doesn't hop over to the next community. And there's this optimal regime where there's the explosion of contagion, I'd call it, where it spreads across both communities and infects all of them. And this behavior is unique to complex contagion. Simple contagion doesn't exhibit this optimal modularity phenomena. Okay. So what did I do? This was run on a linear threshold model, which is a complex contagion model. What did we do? We did the same thing, but instead of running a linear threshold model, we ran the belief network model. So each of these individuals had belief systems of different kinds, and we ran it, and we see the same sort of optimal modularity phenomena, where when you have too much mixing, the beliefs don't spread. Too little mixing, the belief spreads only within one community. And just the optimal amount of mixing, it spreads between both communities. And that's more proof that because this is unique to complex contagion, that's more proof that our model is capable of exhibiting complex contagion also. And we have similar curves for simple contagion, which is a trivial case actually, but I'm not showing it in the interest of time. So that is it. To break it down, you have stabilizing influence to an unstable belief system. It's very easy for this unstable belief system to flip. That's a simple contagion-like phenomena. And on the other side, when you have a stable belief system and an unstable and a destabilizing influence, you have complex contagion phenomena, where you need a lot of reinforcement for this belief system to flip. Okay. So to summarize, we built that weighted belief network model, which doesn't assume simple or complex contagion dynamics, but it allows them to emerge from organic cognitive principles. And what we are up to right now is empirical validation of this model. And I can pause here. I have a few thoughts about empirical validation, which is pretty cool. But yeah, I can pause here for questions and a discussion maybe.
Right, thank you. Thank you very much for this very interesting talk. Are there any questions?
I have a question, but it's about the empirical validation, so we can.
Yeah, if you can tell me the question about empirical validation, then maybe I can do the next part.
My question is, how can you construct the network?
Perfect.
Yes.
Perfect. Awesome. Perfect. That's been my life the past couple of months. Yeah, that's probably also what made me a candidate instead of a student, because that is one of my questions for my exams. Cool. So basically, that means to say you can be my advisor. Okay, cool, great. So maybe we move on to that then, if that's okay.
Yes.
Okay, cool. I'm going to rush a little bit over here, and maybe you can pause me if something is not clear, because I think it's a little trivial, all of these things. So yeah, the question is, how do we infer these belief systems from individuals or communities and social media data? Right? So the belief system I'm going to target to infer, or I want to infer, this is an example, is this sort of belief system. I have Trump, I have vaccines, and I have good, the concept of good. So I want to infer the colors of these edges.
Okay.
Okay. This is an example, can be anything. So what these edges mean is vaccines are good and bad, good or bad. Trump is good or bad. And I believe, or the individual believes, Trump is in favor of or against vaccines. Okay. That one over there. Okay. So that's there. And why don't we ask them? We just ask, we just pull in individuals, ask them, hey, tell us your belief system. But obviously this is a little flawed because social desirability bias and stuff like that. And there is work which shows that as soon as you ask them something, if there's dissonance, it's going to flip. It's going to become stable. Yeah.
It's like it's not static, it's changing time. Okay.
Exactly. As soon as you ask them, it's gone. It's like a quantum mechanical thing where you observe and it's all fun. Oh, my bad. I shouldn't have used. So why don't we ask the others? You call some other people, you ask them you show them their Twitter feed and ask them, what's up? Tell me the belief system of this person. Cool. I mean, there's nothing wrong with this. It's just expensive. And you keep doing this for like any sort of belief system you want. Surveys and questionnaires have their own limitations. And some of my collaborators are also taking down this, are doing this part of things. But that's not my thing. So where I come in is, why don't we ask a machine? Of course, right? You ask a machine, you train an advanced machine learning classifier, which is basically glorified logistic regression. And you gather a bunch of feeds between vaccines and the concept of good. You train a classifier. You gather between Trump and good, train a classifier. Gather between this one, train a classifier. So you have 3 models popping up from that, right? And then you can go on and do this. But of course, you need a lot of label data for this. And models trained for this edge doesn't really generalize to the other 2 edges. So it's not very adaptive, those models. And bigger belief systems need more models. And this is like so not cool in the sense it's so old school and I don't like it. So that's where my current work is going into. I think I'm using large language models. And by large language models I'm talking about post-transformer era of language models. You guys must have seen GPT-3 doing weird stuff on the internet. But this is how you can think. So the easiest interpretation of a language model is to treat it as a human in some sense. So you give it a sentence, you ask it, translate English to German, this is good, and it translates it for you. You give it another sentence, this cola means, tell me if this is a linguistically valid sentence or something like that. And it says it's not acceptable. And this is like sentence similarity. You give it these 2 sentences and it gives you a score about how similar these 2 sentences are. Okay, and then you give it a story, you ask it to summarize, it tells you summary of the sentence. So this is a language model. T5 is one example of a language model. It's not the only one. But what is interesting to me is this language model is not explicitly trained on this task. This is an emergent property of a language model. What it's in fact trained on is some sort of self-supervised training. You gather a bunch of Wikipedia text or text from any digital platform, and you mask out certain words and you train it to fill out those certain words. So in doing this, the language model has not really been explicitly trained on translation tasks or summarization tasks. It's just been trained on a simple task of, filling in the blank. Okay. And because of just this and distributed word representations, that's a cool term, which I throw at her every now and then. But because of that, there are these emergent properties which it's magically capable of capturing. Well, it's not magic. If you really go into the literature, you sort of begin to understand these things. But that's the task it's trained on. That's the point I'm trying to make, saying that I'm not explicitly trained it for a downstream task. It's just a very generic task. So yeah, that's called pre-training, where I give it a bunch of sentences. I ask it to fill in the words, the blanks over here, the M's. Okay. And conventionally, once this model has been pre-trained, you ask it, you fine-tune it to a downstream task in hand. So this downstream task is question answering. And you get a bunch of labeled data for question answering. And you fine-tune this. So this is very different than training it from scratch. So training it from scratch, like a couple of slides ago, it has those limitations. But over here, you're just fine-tuning it. So it has still all the other abilities, but abilities of translation, summarization, etc. But you're also fine-tuned it for your task in hand. But this requires much lesser training data than training a classifier from scratch. But still, whenever there's training data required or whenever there's annotated data required, I tend to like, oh my God, I don't want to get into this. Okay, so one thing which recent language models have been capable of is doing zero-shot inference. That means I just take this language model, trained on this task. It's oblivious to the downstream task. And I can literally ask it this sort of question. I feed it a tweet. The tweet is, I love vaccines. And the options are vaccines are good or bad. That's the option I give it. And I ask it to tell me if it's true or false. And it's capable of doing this. I'm skipping a bunch of details over here, but like a bunch of details, like 3 months worth of details, but it's capable of doing this. BART is yet another language model. It's just not T5. There are other kinds of language models. And it's capable of doing this. And this is it. If it can do this for me, I get it. So this is like an edge, right, between vaccines and good. And that's exactly, okay, so that's exactly what I do. And of course, there are, I can say that it does this, but I've also performed some evaluation to show that it's capable of doing this in a justifiable and good manner and stuff. And that's what I do. And how do I do that is, I'm going to show you how I implemented this right now. So I first, to show proof of concept, I gathered tweets from pro and anti-vaccine communities in Covaxi data. So Covaxi is like a data set which our lab collected quite recently. So we have access to data set. It's a bunch of tweets revolving around the vaccine conversation. And what I first do is identify two communities, pro and anti-vaccine communities in that. And there are multiple ways to do this. The simplest way to show proof of concept is I started from some seed users, which have been identified in literature to be, anti-vaccine users. Those are indicated in black over here. And I got their first nearest neighbors, second nearest neighbors, and third nearest neighbors in terms of retweet network. Okay, so if I retweet a person, that becomes my first nearest neighbor. If that person is retweeted by someone else, that becomes my second nearest neighbor, and I do this. Okay, and I do this, and I perform like a K-core on that to get a cluster of users. And I manually inspect that cluster to show that they're indeed anti-vaccine cluster. Is this clear? This is nothing. This is not rocket science as such. It's simply taking a bunch of seed users, seeing their nearest neighborhood, and manually inspecting if the tweets exchanged among the set of users is truly anti-vaccine or not. Just to like know for myself that it's an anti-vaccine community. And I did the same thing for pro-vaccine community. Okay, I got another seed set of users, got their neighborhoods, and I verified their tweets. So now that I know for a fact that these are pro and anti-vaccine communities, it remains for me to test if my tool works on these communities. So coming back, I need to infer these belief systems of these communities. I can do this at an individual level or at the community level. What I'm showing you over here is at the community level. So I need to infer this. And that means if I have to infer this edge between vaccines and good, I can feed from that community. I can take all the tweets in that community. And for each tweet, I can ask my machine, is this vaccines are good or vaccines are bad? Okay. And I have a bunch of other prompts also. It's more or less semantically sensible, but for the machine, it's like 3 different things in some sense. So I do this for the other edges also. Trump is good, Trump is bad. Trump believes in vaccines, Trump doesn't believe in vaccines. And I ask it true or false questions, basically. And I evaluate this. There's a bunch of evaluation tasks which I'm skipping. But at the end of the day, this is what results for those communities. So between the period of 28 December to 11th Jan, the pro-vaccine community identified has this belief system. The anti-vaccine community has this belief system. And for another time period, it has different belief systems, the same community. Okay, so this is interesting. This is where the work stands right now, but I can explain what's happening over here. So this is when Trump was still in power, and this is when Biden is in power. Okay, so when Trump is in power, this is very early in the vaccine rollout stage. So Operation Warp Speed was a thing in America, where they were trying to get vaccines rolled out as much as possible. And Trump was actually spearheading that effort. So there was discussions of Operation Warp Speed almost every other day. Okay, and you can see that the pro-vaccine community loves him for that. Okay, they believe that Trump supports the vaccines, and they believe that vaccines are good because it's a pro-vaccine community already. And they also believe that Trump is good because logically it makes sense. Okay, the anti-vaccine community hates Trump for that. They say Trump is bad. Vaccines are bad, of course, because it's anti-vaccine community, and Trump supports the vaccines. That's why Trump is bad. Cool. And on the other side, later on, the pro-vaccine community says that vaccines are good. This is when Biden is in power, yes? And Trump didn't support the vaccines, and Trump is bad. Okay. And this again, later on says Trump is bad, vaccines are bad, Trump didn't support the vaccine. This is like a weakly unstable system. That's why this dotted line over here. It's like all three are enemies in some sense. Okay, so this is the belief system of the communities from the data set. And this is, right now we're like evaluating the trustworthiness of these belief systems, and we're actually using human annotators, etc., to go through these tweets and give us these things, and it seems promising at the moment. So yeah, that's how you identify belief systems. You just ask the large language model, and it does miracles, I think.
Really interesting. Really interesting. I heard a bit about BART, but I'm not in social stuff. But it's really nice.
Yeah, this is mostly so for me. So I'm in the space. So I don't think social scientists are using this yet. So I read a lot of computer science literature, especially natural language processing literature.
Yeah, natural language.
Yeah,
yes.
To get into this, and I think that there's this huge field of literature in NLP which has not been used for our kind of work, network science kind of work, which is, and I'm hoping that'll change. And I was surprised too. Like, I mean, and the idea was to try the simplest thing possible, and the simplest thing possible is what seemed to work very well.
Yes.
Yeah. Okay, so that is most of what I wanted to talk about, I think. And I can also, I also built like okay, cool. Questions first, and I can talk more later. Yeah.
Okay, any other questions? May I ask a question myself? So previously you just introduced the how you determine the belief system using the data, but the example is like you determine the belief system of a group, anti-vaccine group or pro-vaccine group. So how would you, after you obtain this belief system of a group, how would you use it later to on your previous network? Because like previous, you have in some sense a network of a network, right? You have a belief network, and you put this in a real social or some real networks. So if you have the belief system of a group, what is a network then? What is a social network in this sense?
Yeah, so what I showed you right now, that's a tricky question to answer. I've been thinking about it quite a bit. So what I showed you right now is at the community level resolution, like at a group level, but nothing says that I can't do it at an individual level. The reason I did it at the group level was to keep the time period short and get a lot of data. So I could have just taken a single individual, seen his belief system. It would have just been a little noisy unless I find these individuals who have a lot of tweets per day. So once I do, my bad. So once I do it, I don't know if that's a question or. Okay, cool. Fine. So once I do it it's the same. I just take an individual, get its tweets, see the belief system of that individual, and then I can construct the social neighborhood of that belief system and then do it. But that's my work for the next 2 or 3 years, I think.
Okay. So like your previous theoretical part is more like the belief system is assumed on one person, and only 3 believe. It's a triad.
Yeah, it's a triad.
Okay.
But most of these things are just the simplest versions possible to capture the most fundamental thing. And of course, it need not be a triad. It can be like, and these machines which I spoke about, you can literally ask them also, give me the most important concepts of this conversation, and it'll output like Trump, vaccines, something else, and all of those things. It takes a little bit of tweaking around, but it doesn't take training. That's the thing I'm trying to point out here. I don't need data to do this. I need a little bit of understanding of how things go around over there. Like, how do I pose that question to that language model is a tricky part. This entire space of prompt tuning and template tuning, etc., is an NLP thing. Yeah.
Okay, great, thanks.
Yeah.
Sorry, previously, I don't know if that's a question or some random noise. Are there any other questions?
Actually, I was interested but the other part that you were saying, like from Python to Julia.
So
I was curious to know what was your view on this, because I still I'm using Python. I wanted to start using Julia.
Okay.
Yeah.
Cool. That's the remaining 3 or 4 slides of my talk, I think, if you don't mind. Cool.
Yes.
So the technical challenge, I showed you the figure of optimal modularity over here, this top right figure over that. Okay, this seems very neat and very nice, but it's a pain to generate because it takes a lot of compute power. And that's the same plot over here. And these are some, early stages of, these are all wrong. It doesn't look anything like this because I was searching in the wrong parameter space. So we've all searched parameter spaces. We've all had that infinite ranges in all dimensions possible and stuff. And this grows with the number of parameters. And this, when they're on, all of these plots are with Python. And this one over here is with Julia. So meaning to say, I'm going to tell you a little bit of story over here. So this is my brain during the early stages of the project, because I had heard that Julia is quite fast. Of course, it's not as fast as C or C++, or maybe it comes close. But the benefit of Julia is it feels like Python when you code in it. It's English and it makes sense and all of those things. And it doesn't have these weird C and C++ old school artifacts in it, right? So it seems very easy to code in, and it is. But I think the main part of Julia for me, which was a challenge, was finding good documentation for it, because I was spoiled by Python. I was spoiled by Stack, where I can just Google a question and the first answer on Stack is right. That's not there for Julia yet. And that's also like a scope for us to improve, I think, because when I was working with Julia, I myself posted a lot of answers on Stack on the forums to help others out, I think. But I'm going to get to that. So in fact, Julia was never my idea in the first place. This was YY in our weekly meetings, asking me if there's any luck with the results, and me saying, Python is too slow, not enough results. I mean, I wait for a week to show you like one plot. It's not enough. And of course, the natural part was like to use the supercomputers, parallelization, etc. But yeah, those have its own learning curve. But YY's suggestion was, just try with Julia. And it was fairly easy to like transfer code from Python to Julia. I didn't use an automatic converter or something. I actually wrote code from scratch. And this served 2 purposes. Number one is it verified that my code in Python was correct, because both these codes are producing similar results. And plus it had also, like working with YY, he goes through code, he does code review and stuff like that. So that is also helpful. And Julia also has these resources like a Jupyter notebook, etc., where you can play around with Julia code. So it's as easy to use as Python. And one of the things which I started doing as I went along Julia is I started documenting maps from Python to Julia. So for example, if I want to generate random numbers, how do I do it in Julia? If I want to do network stuff like drawing, adding an edge, creating a graph from an edge list, it is very hard to find documentation for this, like in one Google search. So I started documenting it myself, and this comes in handy every now and then I go back to. And I think I'm going to put this up somewhere online in a bit. But yeah, this is...
You have to.
Yeah. So this is mostly like, what kind of stuff you go from one to another and stuff like that. And this helps. And I suggest that if you guys work in Julia, I mean, I don't use Julia right now because the expensive parts of my projects are done. But when I did it, it certainly helped me to just go back, look here and do this sort of stuff. What I usually, my workflow is usually doing all of these things with SnakeMake. I don't know if you guys are aware of SnakeMake. So it's a shameless plug over here, where SnakeMake is a tool for biostatistics people to do their thing. But it's been so popular that every field now sort of uses this. So imagine the use case of SnakeMake is, imagine, for example, this project, you have a script which runs your simulation. And then you have a script which controls the input to that simulation, like the input path, what parameters you want to run it on, where do you want to generate the output. And then you have another script which generates the plots of this output. And then you want to make a workflow of all these things. Like you don't want to like go there into a computer and then sit and press enter or Python run, whatever, at every time you want to do this. And you don't want to manually change all these things every now and then. And Python does, SnakeMake does exactly that. So you have these things called rules in SnakeMake. And you can feed input to a rule and out. You can feed the expected output from a rule. And you can feed which script you want to take the input and produce the output. And it generates intermediate files. Like, for example, you can imagine this to be your simulation results. This to be your simulation itself. So it takes in parameters, it outputs whatever the metrics you want from the simulation, and it stores it in a different file. And then you want another script like a plotting script, which takes that input and generates the plots and puts it in the folder you want it to be in.
Oh.
So SnakeMake automates all this process. And the benefit of SnakeMake is in the backend, it for you constructs two things. One is this sort of dependency tree. It automatically realizes which script depends on which other script. That means if I change one script in between my pipeline, should I rerun all the processes before, or can I just do from that script to the next process? So for example, if I change the simulation script, do I have to rerun everything else before that? Or if I change the plotting script, do I have to rerun the simulation script again? No, right? Because I've just changed the plotting script. So I just need to plot stuff in different. So I don't need to run the simulation again. And SnakeMake automatically realizes this. You don't have to keep track of it in your head. So SnakeMake automatically realizes this and it does it for you. And this is especially useful because more often than not, my weekly meetings used to go like, why don't you change that parameter just by a little? So I didn't want to do these things manually by hand. So I would just go into this input, change that parameter, and let SnakeMake figure it out for me, saying what all in this workflow do I have to run? And it does it, and it gives me an output. In fact, a proper SnakeMake can also write a LaTeX paper for you. Like the final rule can be write a paper, and it'll put figures. It can put figures where you want in the paper. It can control the text and all of those things. So, and this is our lab sort of uses this every now and then. Not every now and then, almost for every project, I think. One very beautiful thing about SnakeMake is anyone who has run parallel programs, like if you want, so, but as an example, you have one plot coming from a set of parameters, and you have the second plot with an independent set of parameters you want to run simultaneously because these two things don't have to depend on each other, right? So usually like the hacky way is to start multiple bash scripts. You write a bash script which starts multiple Python programs simultaneously in multiple parts of your computer or multiple cores, and it runs for each of these parameters. Or, that's the hacky way of doing things. Or you use Python's multi-processing libraries to do these things, which is again hacky. But in SnakeMake, all you have to do is, hey, I have 20 cores available. I have 20 whatever compute powers available. Can you just run this for me? And it will automatically figure out for you which of these things are independent because it has this dependency tree. So it'll tell you that, this plot can be generated independent of that plot, or this simulation can be run simultaneously with another simulation. And it works well. And trust me on this SnakeMake, it has a learning curve. That's the problem. But once you learn it, and it's not like a huge learning curve, just to get a normal thing running, I spent like a good afternoon or 1 or 2 days, but I also had help because other members of the lab use it. So I had help from them, but yeah, just reach out if you want to do SnakeMake stuff, and it's amazing, trust me. The last thing is about large language models. If you want to get into the space, catching up with fundamentals of pre and post transformer era models is easy. People think, oh, NLP is something very complicated, but trust me, it's not. I think for all of us over here who do a little more complicated things than this, it's not at all tricky to understand it, at least read literature and stuff. And there are a lot of great resources. Don't trust all blog posts because most of them are wrong. There are great resources in Stanford, etc., which are trustworthy and you can just learn. But keeping up with literature is tricky, I would say. It's so fast paced that like the last week itself, there was a new language model out and I've been playing around with it. But once you understand the fundamentals, understanding like the newer literature is super easy. And compute power, like the things you see on the internet, GPT-3, it has like 400 GB of RAM, which it requires to run on a computer, which is hard if you don't have GPU access. But BART requires like just a single CPU to start. And all the results which I've shown you is using BART. I have results with using OPT also, which is like the open version of GPT, but I've not shown you that, but all the results are using BART. So I'm saying that people have this tendency saying, let me take the most powerful thing to work, but for our purposes, I think smaller ones are good enough. And just a shameless plug again to end this. So I created one of these tools on Hugging Face. Hugging Face is like a Python library to use these transformer models. It's literally like NumPy or like whatever, Matplotlib, for example, where you just download the library and run the model, but you can also host it and learn from others. And this is like a thing which I created this morning, where I feed it a premise. NetPlace is awesome. NetPlace is an awesome gathering. We should do this more often. And then I compute it and it gives me that, oh, sorry, we should not do this more often. And it says that's incorrect, it's contradiction. And of course, I've cherry picked this example, and we should do this more often, gives me a good NT probability. And this is exactly how I do it. I give it a tweet. I give it, is this pro-vaccine or anti-vaccine? And it gives me 2 scores.
Really nice.
Yeah, and that's exactly what I do. And it's simple, it's neat. And I'm sorry I couldn't really go into depth about Julia, but I hope things were a little clear at least. Yeah.
Yes, this is awesome. Awesome. Thank you very much. And is there any question about this part or anything we want to discuss?
Thank you very much for I don't know the talk. I just wanted to ask you, how long did it take you to switch from Python to Julia? Maybe.
Yeah, not long at all. Not long at all. I mean, I had the Julia code ready in like less than a week, I think. I think most of my time was spent just finding the equivalent functions in Julia. That's most of my time which was spent. If I knew those functions, like if I knew what the equivalent of NumPy was in Julia, I would just like do it within like a day or two. It's just that thing. And the structure of programming for like agent-based simulations, it's especially helpful for agent-based simulations. So you guys need to try it. The structure of programming for that does not change at all. It's more or less the same. The inputs, the outputs, the for loops, the if conditions and stuff, it's more or less the same. It's for agent-based simulations with a lot of parameters, etc. It's super quick. Where I've not found it to be as quick, again, because I might be doing it inefficiently and I've not found a good mapping for it, is when I do network operations on it, I think. Like when I keep adding edges, removing edges and stuff like that, that's a little slow at the moment, I think. But I might be doing it wrong at the end of the day. But given a static network, if I want to run dynamics on that network, it's super quick.
Okay. Thank you. No, I really related with the meme, but it was not my supervisor, but my friend does. No, it's very fast. I mean, and I'm really struggling with simulation. Like they take so long. Yeah. So thank you very much. Really.
Yeah, no. So yeah, don't even think twice. Just like get into Julia, code your program in that. It's a good practice, I think. Because I was confused. Do I use supercomputers? Do I try to parallelize it and all of those things? It just required me shifting to Julia and make this thing.
It's not always possible to parallelize a problem.
Yeah,
it's
exactly.
Not always like that.
Yeah. So
sometimes you have to follow the hard path, and in that case, maybe better to change.
Yeah, and I wouldn't even be surprised if, so this was, I don't know, a couple of months ago, or maybe a year ago. I've lost track of time, as we all do. I'm sure that the documentation is so much more better than what it was 12 months ago. It's because I clearly remember, in fact, some of my questions which I posted on the forum went directly to like the creators of some Julia pipelines, and they would quickly answer. And there's like JuliaCon, just like PyCon, where new things are happening. And all it requires out of you is to be in a very bad state where your work is not progressing because of Python. And if you're there, Julia is your answer, I think, especially if it's agent-based simulations. Trust me, yeah.
I mean, yeah, maybe I can share a little bit of experience of myself using Julia, because I'm also a pro Julia person. So I think first I heard of Julia almost 3 or 4 years ago when I was still an undergraduate, and that time we're following a study of some machine learning related model, and the algorithm was implemented in Julia. That was almost 4 years ago. And at that time, the version of Julia is still 0.3. So it's very early stage, and it's quite messy because at that time I was really struggling with this version, because the code requires a specific version of the library or the package. And if you have a newer one or older one, it doesn't work. The code does not run. So that's the very first time I heard of Julia, but I did not use it at that moment. And later, when I started doing my PhD, I have to, because first of all, I'm not good at writing C, although it's fast. And I also have some tasks that needs such kind of performance. For example, I'm running this search algorithm, search a tree or a graph. This kind of cannot be parallelized. And yeah, it's a sequential job. And if you're writing in C, it's fast indeed, but it definitely takes me much more longer time to debug the code. Yeah. So I start using Julia, and indeed it works very well. So for me now, I'm basically using Julia for the sequential job and this kind of easy parallel job, like a Monte Carlo simulation. You need to run the same thing, but with different set of parameters, and you can parallelize it very, very simply, just at one line code. That's like a parallelized version of for loop. You can directly parallelize it. If you know they are not, like, the results are not interact with each other in different loops. And the other thing that I'm not really comfortable with, also because the library and documentation, especially some new, because there are many new libraries that have been developed recently. And but the documentation or function of them might not be very stable compared to Python. So I'm a little bit concerned about if you need to rely on a specific package, specific library in Python, and when you switch to Julia, you may need to check a little bit if there have anything related, anything similar in Julia. And also for like the Stack Overflow thing, if you need to find a solution for your specific question, maybe indeed Julia is not as convenient as Python, because there are so many answers, so many questions. But I found the community is very nice, because there was a Slack channel for Julia users. There's quite a huge Slack channel, and there are many different topics you can join these different groups. And the people there are very helpful. Like if you post a question you have about how should I implement this in Julia, and maybe less than 12 hours or in one day, you can get some feedback from the people there. And for most times, it's very helpful to me. So I think it's pretty nice to join in the Julia community for your work, as is my personal experience.
Yeah, just to put, that was great. Just to put Annalise at little ease that Julia is not hard. This is exactly how Julia code looks. It's exactly looks like Python code at the end of the day. Yes. You have if-else conditions, you have node, for, and that's pretty much it. And these are all just Julia codes. And one thing cool about Julia is you have these special characters you can use, as variable names. Yeah. So that should push you a little more, to
kind of very
definitely
cool.
I always hate when I need to call Greek letter with the entire name rather than the
alpha.
Yeah, exactly. Yeah. So that should push you towards Julia right there. Yeah.
That's also the other comment of Julia. basically the grammar is simple in the sense that it's very close to Python, and I think it's closer to MATLAB because it starts indexing from 1, not 0. And but I saw on the Julia documentation, they have this performance tips. So although the grammar is very similar, but when you switch, you may need to rethink a little bit of the way of writing the code, because due to some specific feature of Julia, you should not use exactly the same logic of writing MATLAB code to write Julia code. I mean, if you want to make it fast. If you want to make it work, then you can almost copy paste from MATLAB to Julia and change some bracket thing. But if you want to make it very fast, and you may need to follow a little bit of the performance tips specifically for Julia.
Yeah, that is true. I ran into this when I was switching also. And my first thought was like, okay, let me just do what I think is easy and see if it's fast enough for me. And it was fast enough for me. And that just convinced me saying, okay, I don't want to make it faster, but I'm sure it's not the most efficient code I've written. And it's probably also why when you have dynamic network stuff happening, my Julia code right now is slow because I've probably not used those performance tips of Julia's. But I think for agent-based simulation, if you have Python script, it's fast enough, but maybe not the fastest possible with Julia, I think, when you transfer. And I think I'm on the Slack community also. Julia. Yeah.
All right, that's great. I mean, any other questions? Any other thing you want to discuss here? I mean, good, very useful discussion.
I hope so. Yeah. Thank you. Thanks for having me, and this is great. Good fun.
Right. If there's no other questions, maybe we could end this event. And by the way, let me ask that if you mind uploading the full recording on YouTube.
Yeah, I don't mind.
Okay.
No. I'm gonna shamelessly plug it in my next talk.
If there's a no, then yeah, I will upload it tomorrow to YouTube.
Yeah,
great.
No problem. Yeah.
Great. Awesome. Then if there's nothing else to discuss, I would like to end this session. And thank you so much. Ratchet, right? Ratchet.
Yeah.
Sorry.
I like how that is on video. Nice.
All right.
So the H is silent, right?
Ratchet.
Yeah. Okay. Ratchet. Thank you so much.
Yeah.
For coming, and sorry for mispronouncing your name.
I don't mind at all. To be honest, it's fun. It's good fun.
Oh. Yeah. Awesome. Thank you very much, and see you
guys.
on the next event. Bye.
Yeah, we'll keep in touch. Yeah. Bye.
Yeah. Great. Bye.
Bye, Rachid.